Alright, so this section we're going to start is, so we had multivariable functions. We can find the first derivative of multivariable function called first order derivatives, second derivatives of multivariable functions called second order partial derivatives. Just like with the one variable case, the next step is to find critical values and maximums and minimums. And so that's what the next set of notes is over, finding the critical values and then determining if those critical values are maximums or minimums in the two variable case. Now, the definitions are similar. The difference is it's a little more complex because we're now looking at multivariable functions, functions in 3 dimensions in this case. Alright, so there are 3 dimensions because there's an x, a y, and a z. Alright, so it would be in 3D. Alright, there'd be an x-axis, a y-axis, and a z-axis. And so relative maximum is, just a point on my curve. So point AB would be my point in the domain of f of x if that point's bigger than all of the points around it. Right, that's what the circular disk means. It means it's bigger than all of the points around it, so there's like a peak to it. Again, it comes out more like a mountaintop or, again, a hill. Alright, so that's what they mean by... Now, outside of that circular area, it might get bigger, but in this point, that function value is the biggest for all the surrounding area. Same thing for the minimum. Minimum would be more of a valley type area. Again, a circular disk means because it's in 3 dimensions, this would be the smallest point, right, in the area surrounding it. So again, like I said, it's like a valley. I'm going to pop to the book. The book has some nice 3-dimensional pictures if you go look. And so I'm going to go pop and look at the book. And so this is what we mean by in 3 dimensions. All right, so specifically looking at this one down here, talking about relative extrema. All right, so see how it's like it's got a mountaintop or like a hilltop. And so that would be a maximum. There's also a little maximum here, so those would be my maximums. And then down here would be my minimum, right? That would be my minimum value. And again, it's in 3 dimensions. There are 3 axes. There's a z going up, x coming out at you, and a y coming out at you. And so that's what we mean by max and mins in 3 dimensions. Relative max, relative minimums in 3 dimensions. Alright, absolute would be the singular biggest. Oops, too far. The singular biggest one. So again, the biggest maximum value on the domain. Just like the one variable case, it would be over the entire function, or at least over the part of the function we're interested in, it would be the biggest peak. Or the smallest peak if we're looking for a minimum. Again, it's the same as one variable functions, it's just now in 3 dimensions instead of 2 dimensions, alright? And again, it would represent, again, a 3-dimensional object, so it would be an object in a 3-dimensional plane, alright, where I've got peaks and valleys. Alright, just like in our one-dimensional case, we can only have relative extrema at a point in my domain, so AB would be my xy. Alright, that point has to be in the domain of the function, and that point's a critical value. Alright, so how do we find critical values for multivariable functions? Alright, well, if you remember, for single variable functions, critical values occurred when my derivative was 0, right? My function has a slope of 0, comes to a stop, or my derivative doesn't exist. Multivariable functions are tough enough. We're only going to look at the 0 case. We're not going to look at any special cases. And so the critical points we're going to be looking at are when we get zeros. And again, as it turns out, for multivariable functions, this is just a little more complex because there are 2 derivatives, 2 slopes I have to find. So critical point of functions with 2 variables can only occur at values in the domain, the values where both the first order derivatives are 0. So it's stopping in the x direction and in the y direction at the same time. There may be other places on the curve where x stops but y doesn't, or y stops and x doesn't. We want to find the points where both derivatives are 0 at the same time. My first order derivative with respect to x is 0, and at the same point, my first order derivative with respect to y. And so if I go back to that picture I showed you before, that's the one sort of up here at the little slightly above. And so these are the points we're looking at. All right, when I get a peak I'm stopped in the x direction and I'm stopped in the y direction, and so there's two slopes. It's sort of a plane, right? Instead of a single line, I've got two lines where I've got to find 0. And the same thing's true in the minimum case, right? My stopping point is where both of them are 0 at the same time. All right, so what we have to do, we have to solve a system of equations. So there's a bit more algebra to be done in these cases. All right, I have to take my first order derivatives, set them equal to 0. All right, so always do that first. All right, all my math that I do from that point on only works if I've set both my first order derivatives equal to 0. And then you've got three methods that you can use. The first one is substitution. It will always work. All right, so you can always use substitution. You should recall it from algebra. You pick one equation and solve for one of your variables. So you pick equation 1, solve for x. Plug that expression into the other equation for that x value. Now you should have one equation with one variable that you can solve, right, with using whatever method you need to solve. All right, once you find that, then you do have a second substitution where once you find, so suppose you solve for y, so y is 10. Well, you plug y back into the original one to find your x value. Right, and we'll practice this. We'll do an example where we do this. Another case is if my critical values come out linear, meaning when I solve these, I can solve these with a matrix. My calculator can do the algebra for me. Yeah, you can always use substitution. Substitution will always work. But in this special case, and a lot of ours will be this special case, right, if I can rewrite my partial derivatives in the form number times x plus a number times y equals a constant. So a, b, and c are constants, and that's a linear equation in standard form. If I can write them in that form, I can then use my calculator to solve. I can use my matrix key on my calculator and solve it, and I'll remind you, or I'll go over how to do that on a calculator. Alright, the last one's not really a method, it's more of a note. Alright, if the first order partial derivatives are in terms of only one variable, so suppose I find the derivative with respect to x and there are only x values in it, well, I just solve for x. And if I find the first derivative with respect to y and there are only y values in it, I solve for y. And you don't have to do any substitution or matrix method. You just solve accordingly. Solve for x, solve for y in the two equations. All right, and we'll do an example of each of the cases. All right, so now we're going to find our critical values. All right, find our first order derivatives, set them equal to 0, and then solve using one of those three methods. All right, find the derivative with respect to x, find the derivative with respect to y. Alright, so first the derivative with respect to x. There's only the two x terms, so the derivative of x squared is 2x. That zeroes away. Negative 52, and the rest zeroes out. And again, set it equal to 0. Otherwise, you can't do the math. Alright, now the derivative with respect to y. There are only the two y parts, so the derivative with respect to y is 2y plus 134, set it equal to 0. Right, this is that last case, right? If you look here, this only has values of x in it, this only has values of y in it, and so I just solve them accordingly. There's no substitution or matrix method needed. Alright, so I'm just going to solve for x, so add my 52 to the other side, so 2x equals 52. Divide by 2, so my x value is 26. Do the same thing for y. Move the 134 over by subtracting. So 2y equals negative 134. Divide by my 2. And my y value equals negative 67. And so there's my critical point. If I plug in 26 into that equation, my first derivative with respect to x is 0. If I plug in negative 67 into that equation, my first derivative with respect to y is 0, and so my critical value is the point 26, negative 67. Right, which it could be a max or min. I don't know yet. That will be the next set of notes where we determine whether that point is a maximum or minimum. There's a process for that too. Right, but there is my critical value, which may or may not be a max or min. Alright, the next example. Alright, so again, find my first order derivatives with respect to x, with respect to y. Alright, so with respect to x, I get 2x minus 18y, set equal to 0, and then with respect to y, I get 3y squared minus 18x, set it equal to 0. All right, so since I've got this square term, that's a quadratic. All right, so it's not a linear case. And I've got x's and y's in both cases. So unlike the last example, we've got x and y's mixed together in both of my functions. And so I'm going to have to solve by substitution. All right, the first method, solve by substitution. All right, and there's usually not always an easier way to go. Sometimes there is, sometimes there isn't. In this case, there actually is, though. If you look at it, the first equation, this one, is just simply x, simply y. This one has a y squared in it. And so I kind of want to avoid the y squared until the end. And so I'm going to solve this equation, and I'm going to solve it for x. I'm going to replace the x here. So I'm going to solve for x in this equation. Alright, so 2x minus 18y equals 0. So I'm going to move my 18y to the other side. So 2x equals 18y. And so x equals 9 times y. Alright, so I'm going to go here and substitute in for that x value. My x value is equivalent to 9y. So I'm going to replace x with 9y in my other equation. So I've got 3y squared still, minus 18. Instead of x, though, I'm going to replace it with 9 times y, set it equal to 0. Alright, 18 times 9 comes out to 162. Alright, now it's a quadratic. There's different ways to solve a quadratic. You can solve it by factoring, quadratic formula, graph it, and find a 0. This one actually factors nicely. I can pull a 3 out and a y out. When I do, in the first term, I'm still left with a y. 162 divided by 3 comes out 54, and that y I pulled out. And so there are two factors. There's y equals 0, and then there's the y minus 54 equals 0. So y equals 54. So this one has two critical values. One of them's at y equals 0, and one of them's at the y value 54. Well, that's only half the point. To find the other half the point, I have to go plug them into this expression. So when y is 0, well, x will come out 0, right? When I plug 0 in for y, I get 0. When I have 54, well, that one I have to do a little work. My x value is 9 times my y value, so 9 times 54, so my x value is 486. And so this function has two critical values, two stopping points, right, which they could be maxes, they could be mins. One of them is at the origin 0, 0. The other one is, and make sure you're careful, the x value is 486. The y value is 54. It's really easy to flip. If I was going to do something silly, I'd be flipping those around. Alright, so that is where, again, this function has two critical values, which again are either peaks or valleys, or neither. There actually is a neither case too. So again, we'll do that in the next section. Right now we're just practicing finding critical values. Alright, the third example. So I've got my p of xy here. So again, find my first derivative, set them equal to 0, and then we'll figure out how we solve them from there. Alright, so first derivative with respect to x, negative 8x minus 4y plus 1920, set equal to 0. And then my derivative with respect to y. Negative 12y minus 4x plus 1600. Set it equal to 0. Alright, this is the linear case. You look at these. There's no square term. There's no mixed variables. There's simply x, y's, and a constant. Which means I can write them in the form ax plus by. And I need to write them in that form because that's the form I have to use when I go to my matrix. Alright, so that's my first step, is to write them in that form. Alright, so in this first equation, I'm going to have to move, actually I might move my x and y's over, then I don't have to worry about negative. So I'm going to add my 8x, and I'm going to add my 4y to the other side. And then I'm going to write it down here. So I'm going to write it in order, in this order. So I'm going to have a positive 8x plus a positive 4y equals the constant 1920. And that's just moving stuff to the other side. You could, if you wanted to, you could move the 1920 over, and then they would all be negative. Negative 8x, negative 4y, negative 1920. And that's fine if you do that. perfectly fine. All right, this one, same thing. I'm going to move my 12y and my 4x to the other side. And so when I do that, I'm going to write it down here. And I put it in the right order. X has to come first, so 4x. Then my 12y equals my 1600. Again, same thing. If you move the 1600 over, that would be okay. It'd just be a negative. So it would be negative 4x, negative 12y, negative 1600. All right, this is the form I have to use to plug it into my matrix. All right, what a matrix is, if you don't remember from algebra, it's a rectangular array of numbers where I write my numbers and leave off the variable parts. All right, and so the first column will be x, the second column will be y, and then, so again, these are the x values, the y values, and then the constant that I have them set equal to. All right, and so the first row represents my first equation here, which again, I just write my number. So it would be 8, 4, 19, 20. And the second row would be 4, 12, 1600. And again, they have to be written this way in order for the matrix to work. That's why I have to write them like this. I just can't randomly put numbers in there. I have to have it written in that form. All right, so this is the matrix I'm going to use. The matrix is a 2 by 3, 2 rows, 3 columns. All right, now I'm going to flip over to my calculator to show you how you plug that in your TI-8384. All right, so here's my TI-83 that you can see on my computer. All right, the buttons should all be in similar places as the 84 or 83. All right, this is the screen over here, and so what you do in order to get to matrix, if you look here, it's kind of hard to see on mine because it's so tiny, but if you look at this right here, x to the negative 1, above it is the word matrix in blue. That's where I need to go. So I have to hit the second button and that x to the negative 1. All right, so those are the two buttons. They're shown down here. Those are the two buttons I hit. Second, negative 1 puts me in my matrix. And so this is what should pop up on your home screen. It should have a bunch of things listed, names, math, and edit. And so I've got to scroll over to edit. So I hit my over arrows till I get to edit, and then I pick one of them in the matrix. I'm just going to edit my A, so I'm going to select 1. All right, first thing you do is tell you how big it was. So my matrix I want to be is a 2 by 3. All right, so it should give me the right size. All right, so there, now it's big enough that I can plug. Now I just make sure I'm careful in typing in my number. So it was 8, enter, 4, enter, 19, 20, and then 4, 12, and 1600. All right, which again, down there showing you the buttons I'm hitting. All right. Once I've got my matrix plugged in the edit, right, remember this is edit, I have to quit. I have to leave the matrix key. So you hit second mode to quit. Go back into the matrix. All right, so I'm going to clear this out so you can kind of see the buttons that I'm going to be using now. All right, so second, back into my matrix one more time. Now I'm going to do math on my matrix. So I'm going to go over to the math key. Right, then I actually have to scroll off my page. So I'm going to go down. And what you have to find is that B. RREF. That's what it was called, row reduced echelon form. And it solves a linear system of equations. That's what row reduced echelon form. So I'm going to select RREF. So enter, I'm going to select that one. All right, so now you should have the RREF on your home screen. Now I have to go into matrix one more time and pick my matrix out. All right, so the matrix, oops. All right. I'm going to have to go pick it again because apparently I hit the wrong button, and so give me a second while I do that. Alright, so there it is on my home screen. Alright, one more time into my matrix key. Matrix, pick the name of your matrix. The name of my matrix was just A. That's the one there. Hit enter, and then end parentheses. All right, so now you should have RREF, the matrix A that you typed in. Once you've got that on your home screen here, hit enter, and then it'll solve it for you. All right, so this is what your matrix should look like on your calculator. So I'm going to go back to my notes, and I'm going to write it in. All right, so once I do the RREF, row reduced echelon form, it simplifies the 101020864. And the way the row reduction means, remember this was x, this was y, this was my constant. The first row, 1x, no y, equals 208. So that's telling me my x value is 208. The second row is telling me my y value, because that's where my y value is. My y value is 64. And there it solved the system for me. Now, you could do the substitution method instead. So if you don't like the matrix method, I do just because it allows me not to make any algebraic mistakes. You could use the substitution method. It always works. But for these linear cases, it's just really nice because as long as I type it in my calculator carefully, it'll give me the correct answer without any algebraic errors. All right, so this one has a critical value at the point. 208 is the x value, 64 is the y value. All right, the last one. All right, so our g of xy is this e term. All right, so first thing, find your derivatives. So remember, the derivative of the exponential is first the exponential without changing a thing about it. But then you're not done yet. Then it's times the derivative of the inside with respect to the variable I'm looking at. So times the derivative of this inside with respect to x. Well, the derivative with respect to x is going to give me a 2x. Zeroes out. Minus 6. Zeroes out. All right, and there's my derivative with respect to x. And I'm going to write my derivative with respect to y below that, since I didn't leave myself enough room on the other part. All right, my e term first. Then my derivative with respect to y now. So now I'm looking here and taking my derivative with respect to y. So the y parts are going to give me out 2y plus 2. Right, set them equal to 0. And remember, just like with the one variable case, the e term is never negative or 0. 0 is more important in this case. Never 0. And so the only place I can get a 0 out are on that last term, right, where I've taken the derivative with respect to variables. And so those are the only two places I can get out my critical value. So I'm going to rewrite them down here. The 2x minus 6 can give me out a 0, and the 2y plus 2 can give me out a 0. And then they're just like the first case. X values in this term solve for x, y values in that term solve for y. And so to solve this one for x, I add 6 to the other side, so 2x equals 6. And so my x value is 3. And my y value is negative 1. And so this particular function has a critical value at x is 3, y is negative 1. Right, and that's what its stopping point is, right? It's got a 0 in both directions. All right, we'll finish up. That's the set of notes there. All right, and again, it's not too bad. These aren't too horrible if you got your derivatives right. The next set of notes will be, well, all right, now that we found critical values, we want to determine if they're max, mins, or neithers. And so that'll be the next set of notes.